Okay, Chemistry 1401. This is practice exam 3. Now we're going to move on with question 10. The last video we completed questions 1 through 9. So question 10, if a system does 200 kilojoules of work and releases 800 kilojoules of heat, what is the change in internal energy for the system? So delta E, you'll remember, is going to be equal to heat, Q, plus work, W. And since we're looking at this from the point of view of the system, if the system does 200 kilojoules of work, okay, that means that our W is going to be negative, because when the system is doing the work, the convention is that the sign of work will be negative, and then since heat is being released, so 800 kilojoules of heat is released. So released by the system. So system is releasing 800 kilojoules of heat. We're going to say that our Q will also be negative, right? Because heat is going out of the system. And so when we write our delta E of our system is going to be equal to negative 200 kilojoules plus negative 800 kilojoules, and we get that our delta E of our system is equal to negative 1,000 kilojoules. And so the correct answer is negative 1,000 kilojoules. Question number 11, the specific heat capacity of silver, Ag. So if we write out our specific heat capacity of silver is 0.24 joules per gram degrees Celsius. What amount of energy is required to raise 12.4 grams of silver from 20 to 35 degrees Celsius at constant pressure? So in order for us to determine the amount of energy that's required, we're going to use the formula Q is equal to mass times C, specific heat capacity, times delta T. And so we'll plug in some numbers. The mass of our silver is 12.4 grams. Our specific heat capacity is 0.24 joules per gram degrees Celsius. And our delta T is going to be 35 degrees Celsius. Subtract 20. We'll put a decimal here. 20 degrees Celsius, like that. And let's double check our units. Grams cancel and degrees Celsius cancel, and like that. So we end up with joules. And when you punch all that into your calculator, you end up with an answer that is 45 joules. So Q is equal to 45 joules. This answer right here, keep in mind that you have to have this formula memorized, okay? You have to know, we'll put here, know this formula, okay? For the exam, I'm not going to provide that formula to you. Okay, let's move on to question number 12. Question 12 says, calculate the final temperature of a block of silver. Where am I here? Let's find it in my notes. Calculate the final temperature of a block of solid silver when the silver, which is initially at 0 degrees Celsius, is placed in contact with an equal mass of solid lithium at 45 degrees Celsius. So that means the silver is going to gain heat, right? And the lithium is going to lose heat. Okay, assume heat only transfers between the metals, nothing is lost to the environment around them, and take the molar heat capacity of solid silver to be 25.4 joules per mole Kelvin, and that of solid lithium to be 24.8 joules per mole Kelvin. The easiest way in my mind to solve this problem is that if we're dealing with an equal mass of lithium and silver, why don't we assume that they both have the same mass? Assume both are 1 gram. Okay, so why don't we assume that they're 1 gram with an infinite number of sig figs, right? Because we know that the heat lost by the lithium, let me write it out like this, the Q of the lithium is going to be equal to the heat gained by the silver, isn't it? Right? So we know from our last problem that Q is equal to M times C times delta T. Here we're going to use molar heat capacity. Okay, so I think it might be wise to convert both of these molar heat capacities into specific heat capacities. Now, how would we do that? How would we calculate the C, or the specific heat capacity, for silver? Well, we know that the molar heat capacity is 25.4 joules per mole Kelvin, okay? And did I put the, no, sorry, I'm just double checking here. Silver 25. I'm getting these mixed up, 25.4 and 24.8. Okay, I have the right one here, just double checking. Okay, and we know that 1 mole of silver, and this is just coming from the periodic table, has 107.87 grams of silver. There we go. Okay, so the molar heat capacity for our silver, we get moles canceling out, and I end up with joules per gram Kelvin. So I end up with a specific heat capacity, which is going to be equal to 0.235 joules per gram degrees Celsius. And then I'm going to do the exact same thing for my lithium. So for my lithium, what was it? 24.8. Keep getting these mixed up. Joules per mole Kelvin. Times, and I know that in 1 mole of lithium, I have 6.941 grams, like that. Again, you can see that moles cancel, and I'm left over with my specific heat capacity for my lithium, which is 3.57 joules per gram degrees Celsius, like that. Okay, now that I've got my specific heat capacities for my lithium and my silver calculated, I'm going to go back to this formula right here, and I'm going to plug in my numbers into my formula. So we'll start with the mass of, which one did I start with? I start with the mass of the lithium. All right, so let's see here, negative 1 gram. And again, we'll assume this is 1.000. We'll just assume it's an exact number. So 1 gram of my lithium multiplied by 3.57 joules per gram degrees Celsius. The delta T for my lithium, the final temperature, we don't know, so it's going to be TF. Why don't we just call it X, because they're both reaching the same temperature. So X minus 45 degrees Celsius, which is the initial temperature of the lithium, is going to be equal to 1 gram of my silver multiplied by 0.235 joules per gram degrees Celsius multiplied by X minus, what was it? 0.00 degrees Celsius. Well, that makes the math a little bit easier. Anyhow, I've gone ahead and done all the math here already, and you end up simplifying it, or I ended up simplifying it to negative 3.57 x plus 161 is equal to 0.235 x. There we go. Yep. And then when you solve for x, you get that x is equal to 42.4 degrees Celsius. Now, I simplified that really quickly. I left the units out here a little bit. But anyhow, in the interest of space, but the main idea is just solving for the variable x, which is the final temperature of both of them, which is going to be identical. And what was the hard part here was realizing that in order for me to apply this formula, I had to calculate the specific heat capacity, which is in joules per gram degrees Celsius, and they told us that we have equal masses, and so we could use the molar heat capacities to figure out the specific heat capacities in this problem. Okay, well, let's move on to the next one. Question 13. Give me 1 second here. Which of the following correctly describes the process of melting a block of ice that is initially at minus 5 degrees Celsius? Assume the pressure is a constant 1 atmosphere. Well, remember when we had a heating diagram, okay, and I'll try to draw one the best way I can here. We had heat absorbed on the x-axis like this, and we had temperature on the y-axis. And we said if we start with our solid, we have to warm that solid up. Then we melt that, right? So this would be the melting point or freezing point, however you want to look at it. Then we have to warm that, you have to warm that liquid up. You have to warm the liquid up like this. There we go. So this is a liquid. We heat the liquid up until it reaches here. So this is the boiling point. Okay. And then you can heat up the vapor from there. So you can heat up the gas from there. So if we're taking a block of ice, which is below the freezing point of water, okay, the first thing we have to do is we are going to warm up that block of ice until it gets to what? 0 degrees Celsius, because that is the melting point of water. And so if we look at the possible answers, it says the first one, heat energy warms the ice to 0 degrees Celsius. That's correct. Then melts and warms to 5 degrees Celsius. No, because it's saying here you're just melting. It doesn't say anything about warming it, so that can't be the answer. The next one, the heat energy warms the solid ice to 0. That's true because we go from -5 degrees Celsius and then we have to warm it up to 0, right? That's occurring in this space right here. We're warming the solid, which then is going to melt into liquid water when it's at 0 degrees Celsius. And so this must be our correct answer. If we look at the next one, heat energy melts the ice into water at -5. Well, that's not going to happen because the melting point of water is 0. Heat energy melts the ice into water at -5. No, that's not going to happen. So there's our answer. That's inside the red box. So again, you need to know how to draw a heating curve. So this is a heating curve, and this is the heating curve. You know, I used it for water because I know the melting point and boiling point off by heart. Let's see here. Wow, we just covered this one, didn't we? Consider the following heating curve. Which region represents the boiling of a liquid? Well, we know that A corresponds to a solid. So A is a solid. B, this represents melting. Okay, then once we've converted it all to a liquid, then we heat it up. So we're heating up a liquid. Then it reaches the boiling point. So this is the boiling point of a liquid. And then once you get it into a gas, you can heat that gas up. But the answer is D, would be the region that represents or corresponds to the boiling of a liquid. Number 15, a 151.2 gram sample of formaldehyde is vaporized at its boiling point of 252 Kelvin by the addition of this much energy, 123.37 kilojoules. Determine the enthalpy of vaporization of formaldehyde. Well, I think the easiest thing to do here is just to say, well, we know that the enthalpy of vaporization has units of kilojoules per mole. Okay, the boiling point isn't even necessary here. It just tells us what the boiling point is. But if we want to calculate the delta H of vaporization, we have the amount of energy that's required. All we need are the number of moles. Well, where am I going to get the number of moles? I have the molar mass, I have the mass of my formaldehyde, and I can calculate the molar mass from the molecular formula. Let's do that first. Let's calculate the number of moles of formaldehyde. So H2CO is going to be equal to 151 grams of formaldehyde divided by its molar mass. I've gone ahead and calculated it. It's 30.03. So 30.03 grams per mole. You see that grams cancel. I'm left over with moles, and I end up with 5.035 moles of formaldehyde. 4 sig figs. My delta H of vaporization is going to be equal to the amount of energy, which was 123.37 kilojoules, divided by the number of moles, which is 5.035 moles, and my delta H of vaporization is 24.50 kilojoules per mole. All right, there we go. There's the correct answer. Remember, this is an enthalpy of vaporization. When we're talking about vaporization is another way of saying boiling, right? Boiling. Vaporization is when we're going from a liquid to a gas. And as we saw on the heating curve, if we take a liquid and we warm it up, when we go from a liquid to a gas, there's no temperature change, is there? That's why we don't see delta T in here anywhere. And that's why the units of the enthalpy of vaporization are just the amount of energy per mole, right? It's got nothing to do with the temperature change whatsoever, because all the energy that's going to go into the formaldehyde in the liquid phase, it's all going to go into vaporizing molecules until they're all converted into a gas, and then you can warm up the gas. Question 16. The heat capacity of ethanol is 112 joules per mole Kelvin, and the enthalpy of vaporization of ethanol is 42.2 kilojoules per mole. How much energy is absorbed by 25 grams of ethanol that starts out at 60 degrees Celsius, which is heated to its boiling point, 78.35 degrees Celsius, and is then vaporized? So what we're doing here is kind of a two-stage process, isn't it? Not kind of a two-stage process. It is a two-stage process, right? We're starting with 25 grams of ethanol, right? If this is our temperature, let's say it's in degrees Celsius, and this is our heat absorbed, we're starting with the liquid, aren't we? Right? Because it's originally at 60 degrees Celsius and it doesn't boil till 78.35. So first we're going to warm up that ethanol, right? How do we calculate the amount of heat absorbed during the heating process? Use Q is equal to M times C times delta T. Then it tells us that we're going to vaporize it all at its boiling point. How do we calculate the amount of heat required to vaporize all of it, to get it to go from the liquid to the gaseous phase? Well, we would use Q is equal to delta H of vaporization times the number of moles. Okay, they've given us a molecular formula, they've given us a mass, and so we're going to be able to calculate the number of moles, aren't we? We're going to be able to do everything that we need here. Let's start by calculating the number of moles of ethanol. We have 25.0 grams of ethanol, which I'll abbreviate ETOH, like that. We know that in 1 mole of ethanol, and I've already gone ahead and done the math here, I calculated the molar mass for C2H5O. It's 46.07 grams of ETOH. Like that. You can see that grams cancel. We're left over with the number of moles of ethanol, which is 0.543 moles. Now again, to calculate our total amount of heat absorbed, we're going to use this formula and this formula. Let's see what that'll look like. We're going to have something that looks like this. Q total is going to be equal to M times C times delta T. That's for the heating of the ethanol in the liquid phase, plus delta H of vaporization times number of moles. Now, another thing you want to notice here is that the heat capacity is given in kilojoules per mole, whereas, the enthalpy of vaporization is given in kilojoules per mole, whereas the heat capacity is given in joules, isn't it? So why don't we convert this one? I got a lot of writing on here, don't I? Why don't we convert this one here to kilojoules per mole? So I'll just divide it by 1,000. So that means it's going to be 0.112 kilojoules per mole Kelvin. Okay, because in 1 kilojoule there's 1,000 joules, so we just divide by 1,000. Now we're all set up. Let's plug in some numbers. Our Q total is going to be equal to the mass of the ethanol, which is 25.0 grams, multiplied by the specific heat capacity, oh, I don't even have to use the 25 grams here, do I? I was thinking I'm going to have to convert that into, there we go. So why don't we just use the number of moles? So 0.543 moles, multiplied by my specific heat capacity, which is 0.112 kilojoules per mole Kelvin. There we go. And then our delta T, which is going to be 78.35 degrees Celsius, subtract 60.00 degrees Celsius. Then we're going to add the delta H of vaporization, which was 42.4 kilojoules, multiplied by the number of moles, which was 0. kilojoules per mole, 0.543 moles. I'm running out of space here, aren't I? All right, let's check our units. Moles cancel, so we're left over with kilojoules there. Celsius cancels with Kelvin because they're the same increment of temperature increase. Moles cancel, and I'm left over with kilojoules plus kilojoules. Good. Okay, so if I write out my Q total, it's going to be equal to, what did I get here? I ended up with 1.12 kilojoules plus 22.9 kilojoules, and my Q total is equal to 24.0 kilojoules. So that's how much energy it takes to. Is that not one of the answers? All right, let's just move on. This is the right answer, 24 kilojoules. Looks like it's closest to this one here. Okay, I must have rounded off somewhere. All right, let's move on. Question 17. Which of the following van der Waals forces typically leads to the largest enthalpy of vaporization? Types of van der Waals forces are London forces, or induced dipole forces, whatever you want to call them. Dipole forces, so dipole, and hydrogen bonding. And we know that the strength of these van der Waals forces increases as we go from London forces to hydrogen bonding. And so a covalent bond is not a van der Waals force, right? Not van der Waals force. So we can cross that one out. Gravitation is also not a van der Waals force, okay? Not a van der Waals. But dipole, and hydrogen bonding are. Hydrogen bonding is the stronger of those two. And so that's going to lead to a larger enthalpy of vaporization. If we think about delta H of vaporization is in kilojoules per mole. Remember, this is talking about how much heat is required to take a liquid and convert it to a gas. If we have liquid, what's going to hold the molecules together tighter in a sample? Will it be dipole forces or hydrogen bonding? And the answer is hydrogen bonding, because it's a special class of dipole that's stronger than a typical dipole force. Number 18, which of the following cannot engage in hydrogen bonding? In order for a molecule to exhibit hydrogen bonding, it has to have either a bond between hydrogen and fluorine, a bond between hydrogen and oxygen, or a bond between hydrogen and nitrogen. If I look at HF, the structure of HF is good because there's a bond between hydrogen and fluorine. If I look at water, of course that can hydrogen bond. It's the best hydrogen bonder there is. If I look at ammonia, it can also hydrogen bond. There's 3 bonds between nitrogen and hydrogen. But if I look at methane, it cannot hydrogen bond. There's hydrogens, but there are no oxygens, fluorines, or nitrogens where it is bound to. And so the answer would be methane. Methane is a nonpolar molecule and can only exhibit London forces or induced dipole. London forces only in a sample. Question number 19. Rank the following species in order of increasing molar enthalpy of vaporization. Remember that delta H of vaporization was in the units of kilojoules per mole. So what we're looking for is, which one of these is going to take the most energy to go from a liquid to a gas? If we look at these 4 molecules that are shown here, hydrogen is a nonpolar molecule, right? It's nonpolar. How do I know that? Because the 2 hydrogens are bound together by 1 sigma bond. There's no dipole in that molecule. So it's only going to experience London forces, nothing else. If I look at methanol, CH3OH, it's got an oxygen-hydrogen bond. So it's a polar molecule, and it's capable of hydrogen bonding. So already we know that this molecule is going to have a higher enthalpy of vaporization, right? Because it's got stronger intermolecular forces because of the hydrogen bond. It's going to take more energy to take methanol in the liquid phase and convert it to the gaseous phase than it would hydrogen. The last two, I have sodium chloride. Sodium chloride is ionic, right? Sodium chloride is made of a metal, sodium, and a non-metal, chlorine. It's going to have ionic forces, or electrostatic forces that hold the ions together. It's going to take more energy than a London force or hydrogen bonding to break those ions apart and to convert them into gaseous ions. Okay, so it's an ionic compound, so it's going to be the king of the castle. So that crosses out this one right here. And then we have C2H4. C2H4 is ethylene. You don't have to know the name of ethylene, but you might want to draw the loop. And C2H4 is this molecule right here. There are no polar bonds in ethylene. Okay, there is a slight dipole between carbon and hydrogen, but the difference in electronegativity is only 0.4. And so we say that that's a non-polar bond. Okay, so it's non-polar, but if you want to, so it's only going to experience London forces. But if you compare the London forces in ethylene and those versus hydrogen, ethylene is larger than H2. And so it's going to have a higher boiling point. It's going to take more energy to vaporize ethylene molecules to convert them from the liquid to the gaseous phase. And so we have hydrogen, ethylene, methanol, and then ionic sodium chloride. So again, ionic, H bond for methanol. These two have London forces. Okay, the ethylene, the C2H4, is larger. Question 20. Which of the following species of the four listed would you expect to be most soluble in water? Benzene is C6H6. Even if you were stuck, you're like, I can't come up with a Lewis structure for benzene. No problem, right? Benzene only contains carbon and hydrogen. I've told you this probably many times over the past few weeks. Whenever you have a molecule that contains just carbon and hydrogen, it is a non-polar molecule. So it's only going to have London forces, right? It's going to be non-polar. And since water is polar, and we follow the rule like dissolves like, so that means polar molecules are going to dissolve other polar molecules. This is not going to be polar. Or sorry, it's not going to be soluble in water. Whereas something like ammonia is this molecule, NH3. It has hydrogen bonding, right? It's polar, okay, and it can hydrogen bond. And so since water is polar and can hydrogen bond, ammonia is going to be super soluble in water. Without even looking at the rest, I know it's going to be ammonia. If I look at octane, the same reason as the first one. It only contains carbon and hydrogen. It's non-polar. It's only going to have London forces. It's not going to be soluble in water. In fact, if you've ever spilled gasoline on top of a puddle, the gas station, you probably noticed that the gasoline sits on top. It doesn't mix with water. Octane is found in gasoline. And the last one is oxygen. Oxygen is also a non-polar molecule, right? There's no dipole in O2. Non-polar, right? It is not going to dissolve in water. It can a little bit. If you're like, well, what about the oxygen the fish, breathe? Well, that's a little bit, only a tiny little bit. Okay, and that oxygen is going to solubilize based off of dipole-induced dipole interactions. Anyhow, so ammonia is the winner here. Excuse me. Number 21. Consider the following phase diagram for some hypothetical substance. Which arrow corresponds to the process of freezing? Well, we have our solid, liquid, and gaseous phases here. What's freezing? Freezing is when we go from a liquid to a solid, okay, by a decrease in temperature. Well, if you look at D and C, sorry, D and B rather, the problem with D and B is that both of those lines are vertical. They don't involve a temperature change, okay? So there's no way that those could involve freezing. Another thing that you notice is that if you compare C and A, which are both horizontal, they both involve temperature changes, don't they? But if you look at C, you're going from a solid to a liquid to a gas. That's going to be melting followed by vaporization, whereas A, you're going from a liquid to a solid, right? Like that by decreasing temperature. And so the answer is going to be A. Number 22, this is a definition I told you you have to be aware of. A unit cell is the smallest repeating unit of a crystal lattice. So smallest repeating unit of a crystal lattice. I told you have to know the simple cubic, the body-centered cubic, and the face-centered cubic. So the simple cubic, the body-centered cubic, and the face-centered cubic. I told you have to know about those, specifically those three unit cells only. Number 23, which type of solid is held together only by van der Waals forces? Remember, van der Waals forces are London forces, also known as induced dipole forces. Next are dipole, or H bond, hydrogen bonding. Okay, we have a network crystal. A network crystal is held together by covalent bonds exclusively, isn't it? A network crystal is something like diamond, for example, okay? Or graphite, held together only covalent bonds, so covalent bonds. So that's not a van der Waals force. The next one is a metallic crystal. That's held together by the electron C, so to speak, or metallic, or sometimes we just call them metallic bonds. A molecular crystal and an ionic crystal. Well, an ionic crystal is going to be held together by ionic bonds, but a molecular crystal is going to be held together by intermolecular forces, either London, dipole, or hydrogen bond, right? Because it's just a collection of molecules. All right. Number 24, another problem with some numbers in it. It says here, water has a vapor pressure of 23.8 torr at 25 degrees Celsius and 92.6 torr at 50 degrees Celsius. What's the value of delta H of vaporization for water? This is a problem where we're going to use the Clapeyron equation. Okay, and you would need that equation, which is the ln of P2 over P1 is equal to delta H of vaporization over R, 8.314 joules per mole Kelvin. I'll put it in here, the whole thing. 1 over T1 minus 1 over T2. Okay, so all we have to do is plug in the numbers and solve for delta H of vaporization. Make sure that temperature is in Kelvin. So Kelvin, if we work out these two temperatures in Kelvin, 50 degrees Celsius is 323 Kelvin, and 25, it's going to be 298 Kelvin. Well, with all that in mind, let's plug in some numbers. So we're going to have the ln of 92.6 over 23.8 going to be equal to delta H of vaporization divided by 8.314 joules per mole Kelvin. You notice that all the answers are in kilojoules. So technically, we could take our value and convert it to kilojoules, couldn't we? Why don't we do that? That'll save us a step in the end. So why don't we convert this to times 10 to the negative 3 kilojoules per mole Kelvin, just to save a step at the very end. Then we have 1 over T1, which is 298. Subtract 1 over 323. All right. So we punch all that in. We get that 1.36. And I put it down here, divided by 2.60 times 10 to the negative 4 Kelvin to the negative 1 reciprocal Kelvin is equal to delta H of vaporization divided by 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. You can see that Kelvin cancels out. So the units of temperature cancel out. And I'm left over with a delta H of vaporization, which is equal to 43.5 kilojoules per mole. Delta H of vaporization, 43.5 kilojoules per mole. All right, so Clausius-Clapeyron equation. Make sure you practice using that formula and knowing how to use it. Well, I think the next problem deals with the Clausius-Clapeyron equation too. It says the heat of vaporization of diethyl ether is 26.52 kilojoules per mole. Given that the vapor pressure of diethyl ether is 455 at 20 degrees Celsius, calculate the normal boiling point of diethyl ether. Let's write out our Clausius-Clapeyron equation. So the ln of P2 over P1 is equal to delta H of vaporization divided by our R, 1 over T1, subtract 1 over T2. Well, if we have our T1, or P1, what do we say? Our P1 is 455 torr, and our T1 is 273 plus 20, so that's 293 Kelvin. Our P2, if it's the normal boiling point, this is boiling point at 760 millimeters of mercury. That's at sea level. So our P2 is going to be 760 millimeters of mercury, and our T2 is going to be our unknown, X. Okay, and we have our R. Our delta H of vaporization is given to us in kilojoules per mole. We can either convert it to joules per mole, or we can convert the R to kilojoules. Okay, I'm going to convert the R to kilojoules because that's how we did it in the last problem. So I'll plug in some numbers here. We've got the ln of 760 over 455 is equal to delta H of vaporization, which is 26.52 kilojoules per mole, divided by R, which is 8.314 times 10 to the negative 3 kilojoules per mole Kelvin, 1 over our T1, which was 293 Kelvin, subtract 1 over X, like that. You can already see that kilojoules and moles cancel. We're left over with Kelvin. And I already went ahead and did all the algebra on this one. And you end up solving for X, which is equal to T2, is 307.7 Kelvin, which is the same thing as 34.5 degrees Celsius. So that's our T2, 34.5 degrees Celsius. Clausius-Clapeyron equation, again, make sure you are able to use this formula. Question 26. Which phase change results in a release of energy? If you think back to our heating curve, right, we had some beautiful heating curves before, right? We said heat absorbed over time, and then we had temperature here. First, we take a solid, we warm it up, we reach the melting point. All right, so here we're going from our solid to liquid, and we heat the liquid up, okay, solid, and then we go from a liquid to a gas, and then we heat the gas up like that. Well, this, if we're just going in this direction, right, if you're going from here up and then over and then up, right, this is heat absorbed as we go from left to right across this graph. But if we go in the opposite direction, if we're going in this direction, that's going to be heat released, won't it be? Okay. Let's look. If we're going from a liquid to a gas, right, that's going to be heat absorbed because we're going from left to right. If we go from a solid to a gas, right, we're going from a solid to a gas up here. That's going to be heat absorbed too, right? It takes heat to take a solid and convert it directly to a gas, doesn't it? What if we were going to do a solid to a liquid? Well, that's melting. That requires the absorption of energy, right? Solid to a liquid. But what if we went from a gas to a liquid? Right? That would mean we're going in this direction. We're going from a gas to a liquid, going backwards. Think about it. If you've ever been burned by steam before on your skin, you know that it releases a ton of heat, and that's why you get burned. Okay, so going in the opposite direction, gas to a liquid is going to release heat. Question 27, which compound has the highest boiling point? We have ethanol, hydrofluoric acid or hydrogen fluoride, lithium fluoride, and butane. I'm going to throw this out there to my students. Does anybody have a knee-jerk reaction as to which one of these would have a much higher boiling point than any of the others? There's one that's way off the charts compared to the rest. Way off the charts. Out of sight. I'm sure I have a student who's got a good idea. No, it's not A or B. No. No. It's not HF. It's not HF, and it's not this one. There's one that's way higher than those two. Way off the charts compared to those. Anybody have an idea? Definitely not this. This is a gas. This is a gas at room temperature. Man, this isn't good. This is the last one that everybody picked. Okay, it's going to be this one. It's going to be way, 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 way higher in terms of boiling point than all the rest. I mean, skyrocket compared to the rest. Not even in the same neighborhood. Right? The first compound has an oxygen-hydrogen bond in it. It's capable of hydrogen bonding, which is a pretty strong intermolecular force. HF has a hydrogen-fluorine bond in it. It's also capable of hydrogen bonding. Okay, if I look at this molecule down here, only has carbon and hydrogen and carbon-carbon bonds. I've told you this, now I'm on like probably the 20th time. Whenever you have a molecule that consists of only carbon and hydrogen, it only has London forces. Okay? Lithium is a metal, fluorine is a non-metal. This is an ionic compound. Okay? The intermolecular forces that hold lithium and fluorine together, fluoride together, are ionic bonds. Okay? Ionic. Much stronger than any of these other forces. Okay? Ionic is off the charts compared to London forces, which is the weakest type of intermolecular force in hydrogen bonding. Not even anywhere close. Okay? Give me a thumbs up if you follow me on it now. Lithium fluoride is an ionic compound. Okay, good. All right. Number 28. What's the correct order for these? If we label these, I'm going to give you guys a second to look at it and see if somebody can come up with the correct answer. Let me know if anybody's got an answer. Emil says D. All right, well, let's think about it. Ethanol has an oxygen-hydrogen bond. It can have hydrogen bonding. The next one, methane, only has carbon and hydrogen. It's only going to have London forces, nothing else. Ammonia also has hydrogen bonding, and water also has hydrogen bonding. We got 3 compounds with hydrogen bonding. The thing is, ethanol in water, okay, ethanol is a liquid and water is a liquid. Something that you should know is that ammonia is a gas. So we know it's going to go 2 is the lowest, then 3. Now between water and ethanol, even though water has a lower molar mass, water maximizes its hydrogen bonding potential. Why? Because in water you have 2 hydrogens in 2 lone pairs that are capable of hydrogen bonding. In ethanol, you have 6 hydrogens, okay, and 1 oxygen. You've got 2 lone pairs that are capable of hydrogen bonding, but only this hydrogen is capable of hydrogen bonding. These hydrogens over here, they cannot participate in hydrogen bonding because they're not bound to an oxygen. And so since water maximizes its hydrogen bonding potential, water is going to have the highest boiling point of all, and then ethanol is going to be down here. So it's 2, 3, 1, 4, like that. Question 29 deals with vapor pressures. It says the vapor pressure of 4 different substances at 20 degrees Celsius is given in the table below. What statement about these structures is substances is correct? We're looking for a correct statement. Remember, vapor pressure is the amount of pressure that the molecules in the liquid phase exert on the environment. How hard are they pushing back? Right? Substance number 1 is just like barely pushing back at all, right? This is substance number 1. It's the weakest. If you look at substance number 4, it's the strongest. It's pushing back the most. Then if you look at 3, it's pretty strong. And if you look at number 2, it's a little bit stronger, like that. Okay? So that's how hard they're pushing back against their environment. Now, what they've gone ahead and done here is they've related to surface tension. Let's look at number 1, or A. The surface tension of substance 2 should be greater than that of substance 3. We're comparing the surface tension of substance 2, and should it be greater than that of substance 3? The answer is yes, this is a correct statement. Why? What's surface tension? If we look at all the molecules on the surface, okay, all these molecules that are on the surface, what's keeping them inside is other molecules on the inside that are pulling them down, right? And pulling them sideways. So surface tension is that horizontal force that they feel. If the surface tension is high in substance 2, it's going to have a lower vapor pressure, right? The molecules aren't going to push as hard against the environment. Let's look at what's wrong with all the other answers. The next one says the intermolecular forces between the molecules of substance 2 should be greater than those of substance 1. That's not true. Substance 1 has the greatest intermolecular forces between the molecules. Right? The intermolecular forces are so strong in substance 1 that it has almost no vapor pressure at all. All the molecules are being held back in the liquid phase. The normal boiling point of substance 4 should be greater than that of substance 2. No. The normal boiling point of substance 4 should be less. It's got the highest vapor pressure. It's ready to boil. It's like, hey man, I'm already out here. Right? And then the last one, the heat of vaporization of 3 should be greater than 2. The heat of vaporization of 3 should be less than 2, right? Because the molecules are already much more prone to escape into the gaseous phase, to go from a liquid to a gas. This brings us to the last question on practice exam 3. Lithium crystallizes in a body-centered cubic cell. What is the mass in grams of 1 unit cell? Well, you need to ask yourself, how many atoms are in 1 unit cell in a body-centered cubic? If we have a simple cubic cell, right? We know that in a simple cubic cell, there's going to be a sphere at each corner, right? 1, 2, 3, 4, 5, 6, 7, 8, like that. Okay. Well, remember, we only count the part that's inside the cube. We're going to have 1 here, 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 1 in the back here, 1 here, and 1 here, and 1 here, sorry, like that. So that's a total of 1, 2, 3, 4, 5, 6, 7, 8. I explained to you how each one of those corners, it takes up 1/8 of a sphere. You'd have 1/8 of a sphere times 8 corners. That's in a simple cubic. But in a body-centered cubic, you have a sphere in the center of the body, in the middle. So that means you've got the 8 corners, plus you have that sphere in the middle, plus 1. That gives you 1 plus 1, which is 2. So that means there are 2 atoms, 2 lithium atoms, in the unit cell for a body-centered cubic unit cell. Well, if there's 2 lithium atoms, what's the mass of a lithium atom? I know that the molar mass of lithium is 6.94 grams, but in 1 mole of lithium, I have 6.02 times 10 to the 23 atoms. If I divide that, 6.94 divided by 6.02 times 10 to the 23, I get 1.15 times 10 to the negative 23 grams per atom. Right? That's how much 1 atom weighs. And there's 2 atoms in the unit cell. When I multiply that by 2, I get 2.30 times 10 to the negative 23 grams. That's the mass of 1 unit cell for a body-centered cubic unit cell.